Good evening. Welcome to Satellite Showtime for this Tuesday, April 23rd. We have an exciting show online for you this evening. NASA has high hopes for the 1990s. We'll tell you what that agency is up to. We'll also bring you another segment of Satellite Preview 85. But first, this industry news brought to you through the cooperation of STV Magazine. Members of Congress are waiting to hear your input on two proposed bills. One calls for a 2-year halt to scrambling. The other encourages the development of the home satellite industry. The sponsors of these bills hope together they will give Congress and the Federal Communications Commission time to establish a fair marketing plan for home satellite system owners, so programmers and dish owners can work together for a fair price for programming. The bills are H.R. 1769 and H.R. 1840. If you want to show your support for them, you should contact your congressman or the supporters of the bills. Representative Judd Gregg of New Hampshire introduced H.R. 1769, the anti-scrambling bill. Supporters of it include Charlie Rose of North Carolina and Eugene Chappie of California. And H.R. 1840, the Fair Marketing Bill, was introduced by Representative W.J. Billy Towson of Louisiana and co-sponsored by Ohio's Bob McEwen and Bob Whitaker of Kansas. In just a few days, the FCC is expected to adopt a national policy on zoning. That policy would preempt local zoning ordinances in cases where the zoning is overly restrictive. These news items have been brought to you through the cooperation of STV Magazine. Coming up on Satellite Showtime, what NASA has in store for the 1990s.
Want to know more about satellite TV? Then go to the source for product reviews and how-tos. We're on the road and out in space and sometimes in very cold places, with features and technical reports. It's all in Satellite TV. That's only $19.95 for 12 big issues of STV Magazine. Call now, 1-800-438-2020, and get this LCD calendar clock free with your subscription. That's 12 big issues of STV Magazine and the clock for only $19.95. The number again is 1-800-438-2020. 1-800-438-2020. Call now.
NASA just brought the Space Shuttle Discovery back from its latest mission, but it has more than shuttle flights planned for the future. In the 1990s, the agency is planning to launch something totally new, a self-sufficient space station. There, scientists can carry out a multitude of experiments, all done in a weightless environment. But it will take a number of shuttle flights to construct the station.
This is a film that we put together to examine some early ways in which we might construct the space station that NASA is proposing to build in the early 1990s. As engineers, one of the things that it's very important for us to do is to visualize the thing that we want to end up constructing. That helps us to determine ways in which pieces fit together. It helps us to determine ways in which things will fit into the shuttle, and it helps us to determine potential design problems that we might have before they occur. And we have found that it is very useful for us to use computers to do that. So these scenes were generated by a computer to depict the 7-flight sequence to construct the space station as we currently envision it. What you're seeing now is the remote manipulator arm on the orbiter putting 2 radiator panels in place in what is the first member of the space station we call the transverse beam. This particular concept for the space station, which we have dubbed the power tower, is about 400 feet long and has a transverse beam that's about 260 feet long. Obviously, those are objects which are much too large to put in the shuttle, which would take them to orbit. So they are assembled in a state which has them compressed, and then they will be expanded once they achieve orbit, and that's what this film is now showing you. The 2 objects sticking from the top are the radiators. The 2 objects on the end of the boom, as it's now being deployed, are solar arrays, which are boxed. These are truss members that are being automatically deployed. One of the things that we'll be looking at over the next several years is whether we want to use structures like this which can be deployed, or whether we want to use structures which an astronaut would go out and erect. and I suspect we'll end up using a combination of both. What you're seeing now are the solar arrays being deployed. These are about, each one of these is about 30 feet wide and about 50 to 80 feet long to give us a total power of 75 kilowatts on the initial space station. You can see the array unfolding out of the box as the central beam elongates itself. We've already done one flight experiment on arrays like this on a shuttle flight in mid-1984. This is now the second flight. We also brought up a manipulator which we put on the station, and you can see it there on the transverse beam. The manipulator on the shuttle is taking out the next large element of structure, and we'll attach it to the cross beam that has the arrays and radiators on it, as you can see. We envision this station flying at an altitude of about 250 to 270 nautical miles, which allows it to perform the functions of being a laboratory site, of also being a transportation node. We envision that the station will both service a large number of satellites and then provide for the launch vehicles that launch those satellites back up into higher orbits. That's one of the reasons we are very attracted to this particular configuration of the station. It has so much truss structure that serves as a pegboard, so you have a lot of room to attach things. Now, the manipulator on the station has put the large central beam in place, and it's being deployed. Again, it will probably be some combination of deployed and erected by astronauts. This central beam is about 400 feet long, so it's like a very large radio antenna. These trusses are 9 feet on a side to give you an idea of the scale. There you can see the central beam being deployed from the transverse beam. The things now deploying from the bottom of the central beam are radiators which will radiate heat away from the modules which are added at that lower end of the beam, as you'll see in the next few flights. Now the manipulator on the station is picking up another piece of truss structure, which again is in its compressed state, to take it down, and it will be added to the lower end of the beam. There you can see it moving down. This manipulator on the station runs on rails which are part of, as we envision it now, which are part of the truss structure. One of the things that we'll be studying over the next few years is where the operator of that manipulator would be, whether in the shuttle or out on the station. Certainly an astronaut probably will travel along with it to make sure that it's placing these elements in their proper positions. Now the truss structure is being deployed on the bottom of the large central spine. And again, a lot of this is done for engineering purposes to help us understand the geometries involved. The deployment would not take place that rapidly, obviously, and you can see some pieces now just being put in place that would probably be erected. Now the central core of the station is in place, and the first module has come up on the third flight. The manipulator on the station is picking the module up and will insert it in its final location. It's at this point that the station could be man-tended. Instruments could be put on the station to perform their experiments, and although there aren't enough modules for the station to be permanently manned, there could be astronauts that would come up and read the instruments, resupply materials in the instruments or the experiments, and then return to Earth. So after the third flight, as we currently envision it, the station could be operational and running experiments.